All right, this topic is 1.8 from College Board. It is primary productivity, and it is essential to any ecosystem. And we're talking about kind of this word, which will become a measurement that describes the energy that is coming into an ecosystem by our producers. All right, so primary productivity, it is the rate at which light energy from the sun is converted into chemical potential energy by green plants or by our primary producers. As we know, when sunlight is absorbed by the chlorophyll containing organisms, so those are going to be our plants, our protists, our bacteria, it's then going to be converted into chemical energy through our favorite word, photosynthesis. So here's our equation that we're going to get very used to. CO2 plus H2O plus light energy inside of a chloroplast in a plant is going to turn into a glucose molecule plus an oxygen molecule. So that's what we're going to get from this photosynthesis reaction. All right, now one thing we have to keep in mind are our two laws of thermodynamics. The first law of thermodynamics ensures and reminds us that energy can never be created or destroyed. It has to just change from one form to another form, or is transferred from one thing to another. It cannot just disappear. That means that light energy that's coming in is then going to be turned into chemical energy. It can't just disappear. And then the second one says that whenever an energy is changed from one form to another, unfortunately, some is always going to be lost in the form of heat or friction. So we have to keep these two laws just in mind, and we think about how energy is moving through our ecosystem. The first law of thermodynamics tells us that the energy that the plants absorb during photosynthesis has to go somewhere. It must go somewhere. And in this case, it's going to go from this light energy and it's going to go into chemical energy that's stored in the bonds of this glucose molecule here. So plants can store this energy as glucose initially, but then they're going to convert this glucose into other carbon compounds. And these other carbon compounds allow them to store it. So they can store it as starches, as cellulose, or as lipids. So starches are, for example, we see them in the forms of pasta, beans, potatoes, and so on. So this could be the roots of a vegetable. It could be the grains in a plant. So different parts of the plant become starches. Then we have the cellulose. Cellulose, also parts of the plants. It could be the leaves. The leaves could be the cellulose. It could be some of the fruit that they produce. It also could be the roots in the form of carrots. So these are versions of different cellulose. And then we have lipids. When we think of lipids, most of the time we think of fish. But if we're talking about plants, a lot of the time they're storing lipids in the form of nuts. So different nuts, and this also could be avocado is another example of this. It also could be seeds as well. So that's how they're storing their lipids. So they're going to take this glucose and then convert it to different things. Most of life on Earth is powered by taking these stored carbon compounds and converting them back into CO2 and H2O. This is called respiration. So our respiration equation is just the reverse. So I'm just going to make sure we remember it is the reverse of photosynthesis. Right in there. Okay, awesome. That's going to come back to us. All right, so here we go. We have photosynthesis, the CO2, the H2O, all comes in with light, and we get sugars and we get oxygen. And this is all happening within our leaf. So that happens. We're going to create a lot of sugar. But I think one thing that we forget is that plants also need to go through cellular respiration. It is not just something that herbivores or carnivores go through. Our producers also have to go through cellular respiration, and they do that in order to make more leaves or to make more roots or to make more parts of their plants. So when they do that, they're gonna go through their cellular respiration, and then some of it will be left over. And that leftover will go to the heterotrophs and it will be eaten. All right, so let's talk about this primary productivity and how will we come up with this measurement. So as I mentioned before, primary productivity, this is a measurement. And we're going to start with what we call the gross primary productivity. This is I'm going to call this the total. This is the total energy that plants bring in from the sun. How much glucose can they store? And all of this is what we consider our GPP, or our gross primary productivity. Then they're going to use some of it. Okay, they're going to build their leaves. They're going to make some fruits. So this is everything they use here. So as I mentioned, this is coming in flowers. I'm not going to draw it out for you, but we got flowers. We have roots. We have more stems, more leaves. Every new tissue that they are creating, this is what we're going to subtract. This is where they're going to use their cellular respiration. They're going to take away from their gross primary productivity. When we subtract their cellular respiration from their GPP, we're going to get the NPP, which is our net primary productivity. This is after everything's done, how much energy is left over? How much energy have they produced after they've finished producing everything for themselves? So this here is the energy that is then becomes available for the ecosystem. Wonderful. So just to recap, it is the production of the carbon compounds through photosynthesis. Most importantly, they're producing all the sugars, starches, lipids that support the entire organisms for all of the ecosystem. It's all coming from these primary producers. But to sum up, most important part from this slide is that we found out what our NPP is, which is our net primary productivity, and we learned how that is different from our GPP, which is our gross primary productivity. This being the total, and this being after we subtract everything the plant uses for itself. All right, so this is just a nice little recap of everything that's going on here. And I really want to remind ourselves that photosynthesis happens and we are producing glucose, but then we have our heterotrophs, our herbivores, our primary consumers, and they're doing the complete opposite. It's a complete flipped reaction here. So I think it's very good to see this difference. Okay, so to recap one more time for you, remind ourselves that gross primary productivity, or GPP, is the amount of energy that is converted into sugars through photosynthesis. And we're going to call this the total. Under normal conditions, we're looking at about 1.5% of the solar energy that lands on a plant's surface is captured and turned into sugars. Most of the time, this is measured in units of energy, so this could be joules most of the time, per square meter per unit of time. So this is a lot here. So if you see joules per meter squared per second, so it is energy, let me get my little thing here, energy per space per time. That's how we're going to measure our GPP. All right, now remember that GPP was the total. Now we're getting into our NPP. And this is where we have to do some math. We're going to take our GPP minus the energy lost to respiration. I want to make sure I'm clear here. This is respiration of the plants, not everything else. This is the respiration of just the plants. So our NPP, our net primary productivity, is our GPP minus the energy lost to the respiration. Under ideal conditions, they're going to capture 1.5%. Our NPP is going to turn into about 1%. So that means we're using 0.5% used by the plant for respiration. And we've got the same units as we had before, which was normally joules per meter squared per time. Okay, so GPP and NPP, these can be measured in different terms. And I just want to leave this slide up here because I think it's very helpful because we're going to be using it in APES to look at different measurements and compare different quantities. So we could be looking at amount of oxygen. That's one way to look at it. We could look at the amount of CO2 that's removed from a system. Or we could look at it in terms of the amount of carbon compounds accumulated. Biomass we'll see over and over and over again. So different ways of looking at it. It pretty much has to do with that chemical reaction. So any part of this chemical reaction, whether it is the biomass here, the oxygen produced, the CO2 consumed, or even the water consumed. Those of you who took chemistry remember it's kind of like stoichiometry. So we can use this GPP or NPP to understand how each one of these was either added or taken away from a certain ecosystem. Especially when we're talking about NPP. We are most often, let me highlight it here, we are most often going to be looking at it in terms of biomass because this is the leftover carbon compounds. This is the leftover sugars that were not used. So it's the amount of matter that is present in that collection of organisms is what we call biomass. It's kind of like it's the dry mass of all the organic matter. We often are going to measure it in grams or kilograms. Then not only are we going to use grams or kilograms, but then we're going to put it in per square meter per unit of time. So our units are going to look something crazy like that. So weight per square meter per time, year, week, day, etc. And just as an FYI, we're going to use this a little bit later, but 1 kilogram of biomass is equivalent to 16,000 kilojoules. And you could even go a little bit further and convert that into kilocalories if you wanted to. All right, now we will dive into this a lot later, but this GPP and this NPP of an ecosystem, they're often determined by some very limiting factors and often give us an idea of the status of an ecosystem and how it's doing. So some of these factors that often create it to be higher or lower, for example, are light, obviously because of photosynthesis, temperature. Precipitation, again, because of photosynthesis, water is important. And then the nutrients that are involved in the soil. All of those create either a higher or a lower GPP and MPP. So some terrestrial environments are, especially near the equator, we have a really great NPP. Near the equator, we have a lot of light needed for photosynthesis, a lot of rain also needed for photosynthesis. And so we're going to get so much water, so we have high amounts of plant growth, leading to an increased NPP. Now, on the other hand, it's going to be low at these high latitudes. So this would be the Arctic or the Antarctic. This is because we have low sunlight. Again, that's needed for photosynthesis. It's too cold for plants to survive. And all of those factors contribute to this lower NPP. Another thing we don't think about are our aquatic environments. In our aquatic environments, we actually have some areas of high NPP and some areas of low NPP. So it is extremely low in our open oceans because there's we have no nutrients. All of that dead organisms are sinking to the bottom and they're carrying their nutrients with them. So therefore, there's not a lot available for growth and for continued photosynthesis and for plants to grow. However, on the continental shelves, and these continental shelves, we're talking like by the beaches, very close to land. We have our NPP is going to be a lot higher. And this is because our rivers are bringing in the nutrients. So we've got all these rivers bringing down these nutrients down where the rivers are colliding with the oceans with so many nutrients. And these abundant nutrients are what are causing this high NPP. We can also have some other areas of high NPP where we have upwelling, where we have nutrients that are brought up from below. So we're going to look at ocean currents a lot later, but it's important that you remember that NPP is not the same all throughout the ocean environments. It can change in many different locations. I want to show you this. I like this diagram a lot because it shows you per biome how our NPP is changing. Obviously, we have our tropical rainforest, our swamps, and our estuaries. As we mentioned before, high nutrient, very rich. Our tropical rainforest, these areas are getting so much sun. And so that's increasing the amount of photosynthesis that can happen. So that has a very high NPP up in these three. Those are our top three. On the other side, our tundra, our desert, our open ocean, not as much because they don't have the access to they either don't have the access to the sun or they don't have access to the nutrients needed to grow plants. Now, one thing I think is really interesting is often we see tropical rainforests being torn down for agricultural land, in order to have agricultural land so that people can grow their papayas, their corn, their wheat, whatever it is. And we have to keep in mind, we have to remind ourselves that the NPP, the drop in NPP that happens when we take rainforest and then burn it for agricultural land. Agricultural land has a much lower NPP than tropical rainforest does. And so it's so sad when we see this happening all the time. And many people think, oh, it's a tropical rainforest. It will have so much nutrition in the soil. But no, it's got nothing. NPP doesn't compare in the agricultural land as it does to our tropical rainforests. All right, and that's a wrap. So we'll chat more about this, I'm sure. So see you in class.